So today I want to show that it doesn't really matter what kind of structure we're dealing with when we're looking for reactions, as long as it's statically determinate. Okay, so we don't need to invoke anything around hinges or material properties when we're just looking at three equations of equilibrium in 2D. I want to show that because all we really need to know in this case is where and what are the loads and the moments on that structure, and what the supports are and what that means. If we can draw a free body diagram and only need to find three things, we can solve it no matter what it is. Let's have a look at a structure together. So this is the structure I want to look at. This is a truss. We will discuss these in a lot of detail later on, but just for now, what we can see is this is a structure. It's not a beam, so we might feel a bit less familiar with this one. We do exactly the same that we've done until now. That means, first thing, deciding what the supports are and what forces we need to find for the reaction forces. We can see here that at point A, we've got a pin support. So let's draw in AY and AX. And we can see that, we've got a roller support, only this time it's at a 90-degree angle to what we had before in beams. That means that this is the direction of the reaction, and it is CX. Now, this is a truss. Those black dots are hinges, but since we can see that we have three reactions to find, we really don't need to worry ourselves about what the structure is. Now, the distances in this structure are going to be 2 meters and 3 meters, and I'm using these distances to demonstrate really what distance you need to take each time. So let's go ahead and find the reactions. Let's start off by doing sum of forces in the x direction equals 0, with this being my positive direction. Now actually, interestingly here, I do have more than one unknown. I've got AX plus CX, those are my two unknowns. And then if I look at the forces, I can see here, I've got a force here of 10 kilonewtons and I've got a force here of 15 kilonewtons, both in the positive direction. So plus 10 plus 15 equals 0. I can't really say what AX and CX are, two unknowns and one equation, but what I can say is that AX plus CX equals minus 25. That's as far as I can go now. Let's have a look at the sum of forces in Y. So if I do sum of forces in Y equals 0, with this being my positive direction, I've got AY, so only one unknown. And then if I go to B, I can see that I've got minus 20. If I go to C, I can see that there are no other forces in the Y direction. And at D, I've got minus 5. All that has to equal 0 for it to be in equilibrium. So here I can straight away find AY. You can see that it is 25 kilonewtons. And the last thing that I need to do is sum of moments somewhere. Now I want to choose the point where I can get rid of most of my forces. And that is why I am going to choose point A. So let's see what will contribute to moments in A. Remember, anything passing through A, or anything that its line of action passes through A, cannot contribute a moment because there is no distance, right? Distance is how you create a moment. So I can see here that for this 5, its line of action passes through A, and for this 15, its line of action also passes through A. They won't contribute to moment. What I will have contributing to moment is this 10, this 20, and CX, which means that I will be able to find CX from this. So sum of moments around A equals 0, with this being my positive direction. Let's start off at B. At B, I've got that 20. It is giving me a moment that looks like that, which is a negative moment. So that is minus 20 times the perpendicular distance from its line of action to A, which is 2 meters. If I move on to C, I've also got a negative moment because I can see that the direction of travel is continue along this line of action and then back down to A. So once again, clockwise, so negative. And its distance is the perpendicular distance from that line of action from CX to A. Or in other words, CX is in the X direction. It needs a Y distance to create a moment. That is 3 meters times 3. That's the distance. If I move to D, I've got 10, also negative, so minus 10. And in this case, the distance, 10 is in X, so the distance is in Y, so times 3. And nothing else contributing to the moment, so that equals 0. And I can say that 3CX equals minus 70. So CX equals minus 23.33 kilonewtons. now that I have Cx, I can go back to the connection between Ax and Cx and say that Ax equals minus 25 minus Cx, which is minus 25 minus 23.33, and that gives me minus 1.67 kilonewtons. Let's replace our findings back into the structure and then do a check. So Cx came out negative, meaning we assumed the wrong direction, and actually Cx goes this way and it's 23.33. Ay is in the correct direction and it is 25, and Ax is also in the wrong direction, and so really it is in this direction and is 1.67. And now we're ready to just check our findings. Now, we are going to assume that we assume obviously that we've solved this and we're just checking if this is in equilibrium. I can check if it's in equilibrium by doing, for example, sum of moments around C equals 0, with this being the positive direction. So if I do moments around C, this 10 passes through, so it's not going to contribute, and this 20 also passes through, so it's not going to contribute. So really what we need to consider in this case is this 5, this 15, this 25, and this 1.67. So once again, remember that the distance is the perpendicular distance. So two things you need to find here: direction and distance. The direction of the moment, clockwise, is negative, counterclockwise is positive, and in terms of the distance, it is always the perpendicular distance. So if you have a force in x, you're going to need a distance in y, and if you have a force that is in y, you're going to need a distance in x. Let's work it out. Starting at A, the 25 contributes a clockwise rotation, so it is negative, so minus 25. The distance between its line of action and C is 2 meters, so times 2. The 1.67 contributes a negative moment as well, so minus 1.67, and its distance is 3. Moving on to B, we've got 15 contributing a positive moment. Distance is 3. And at D, we've got 5 also contributing a positive moment, so plus 5 with a distance of 2. And that's all we have. Now, if we've solved correctly, that should equal 0. If we haven't solved correctly, we need to go back and figure where we made a mistake. So let's sum this up. So minus 50 minus 5 plus 45 is 10. So you can see here that we've got minus 55 plus 55, and that is indeed 0. Check complete, and we've solved the reactions, even though we don't yet know how to solve the truss. But that will be in the next series of lectures. So we've solved a structure that looks a bit more complicated, but using exactly the same principles, we've managed to find the reactions. And that's it. Join me for some more structural engineering. Bye for now.